the transformer architecture. Let's see. So Attention is All You Need is a paper that came out in NIPS 2017, and since then there are many applications that have started using the transformer model for language generation, translation, summarization, question answering, image capturing, music generation, and so on, and many more applications, right? So in this video we want to briefly look at the different components in the transformer model at a high level. We'll have a detailed video on each of these later. So essentially there is an encoder side and a decoder side. So the encoder takes in the input and tries to understand the input, while the decoder is actually generating the text. So if you take a machine translation task, one of the primary tasks the initial transformer model was tried on, what you see is that the encoder will take in the input sentence of one language, and the decoder will actually give you the translated text in the target language, right? That's an example use case. Now, what are the different blocks in this transformer? Let's see. So the first is positional encoding. So let's look at how we send input to the transformer. So we typically have, if we have, like, let's say we are using it for text generation of some form, like let's say for machine translation, the input would be a sequence of words, and here you have it could either be word or subword, and there are many different types you can do this, but essentially each token in the input will have some kind of an embedding vector, and then you have a sequence of these vectors, right? And then you have something called a positional encoding vector. The purpose of this is because transformer model is based on the premise of self-attention, and when you're computing self-attention, you're not really giving any importance to the sequence of tokens. And positional encoding is something that helps the transformer model overcome this limitation of not paying attention to the sequence by putting a positional encoding. So the positional encoding is a vector that is uniquely representing the position of a word in the text, right? And we will look at it in more detail in another video. And these two are typically added and given as input to the next component, which is the multi-head attention layer. So the multi-head attention layer itself has multiple heads. In this case, like you can see there are 8 heads, and each head is doing something called the scaled dot product attention. So the scale dot product attention is the thing that is actually enforcing the self-attention mechanism, which enables every token to see the relevance of all the other tokens in the input, right? And we'll not go into a lot of details in this. We'll cover this in another video. And the output from each of these heads is typically concatenated and then given for further processing to other layers, right? The next is layer normalization and skip or residual connections. So normalization typically is done to data sets in machine learning applications where you want to get different inputs to the same scale. Now layer norm is typically applied in deep neural networks to overcome something called the internal covariate shift, which what essentially happens is when you're actually changing the weights in a neural network through the training process, these weights change the activations of subsequent layers, and sometimes the distribution of activation functions is changed, and hence we apply something called a layer norm typically for transformer models, where within a layer all the activations we apply normalization by subtracting the mean and dividing by standard deviation. Then there is also the residual connection. So what we see here is there is this skip connection. The input is directly surpassing this multi-head attention and going to this block, right? That's a skip connection, where what we are doing is we are taking the input to the multi-head attention and adding it and concatenating it to the output, right? And we'll see why we need this in other videos. So the next is a feed-forward network, which we know well about. So a feed-forward network is typically a fully connected network, as you can see here, and there could be dropout connections, of course. And then these are the different components. And you see that these components are pretty much the same set of components that are used even on the decoder side as well, right? And we see the same set of things on the decoder side. So one thing that is different on the decoder side is really the loss function. So the loss function is something, loss layer is something that we need to choose depending on the application at hand. And another interesting part is, here we are using masked multi-head attention instead of just like, the plain multi-head attention. What this means is that when we generate text, right, we apply in the decoder part, typically, at least in the decoder part, we always apply this masking to make sure that we are not looking into the future, right? So these are the various parts of transformer model. Training a transformer model. The training strategy depends on the task at hand. So for different applications, we typically have a different loss function. But when we are talking about training, there are two broad strategies that are used. One is the masked language model, where we actually mask a small percentage of the words in the input text and we try to predict them. And the causal language model, where we are actually trying to predict the next set of words that are generated in an autoregressive fashion. An example of MLM is BERT, and an example of a causal model is GPT. To summarize, we looked at the various blocks in the transformer architecture. We looked at positional encoding, we looked at multi-head attention, we looked at skip connections and layer norm, we looked at feed-forward unit, we looked at masked multi-head attention, and we talked about the loss function. So hope you use transformers in a lot of your applications. Thank you.